Somewhere above a field right now, a blade the length of a football field is slicing through the air at more than 180 miles an hour, and from the ground it looks like it's barely moving. That's the illusion. Something spinning fast enough to kill you in half a second looks, from 300 feet below, like it's asleep. And the strange part is that the wind pushing it isn't even blowing that fast. A turbine can be turning at highway speed on a breeze you'd barely notice on your face. Stand at the base of one of these towers and the size stops making sense. The nacelle alone, that boxy housing at the top, can weigh more than a loaded jumbo jet. The blades below it are longer than the wing of a Boeing 747. And the only thing driving all of that steel and fiberglass around in a circle is air, the same air that couldn't knock a hat off your head a few hundred feet down. So how does slow air make something spin that fast? And once it's spinning, how does moving metal turn into the electricity charging your phone right now, heating your shower, running your fridge while you sleep? That's what's actually happening inside a wind turbine, and almost none of it works the way people assume. Start with the obvious guess, the one almost everyone makes without thinking twice. Wind pushes the blades like a pinwheel. That's wrong, or at least it's only a small piece of the story. If a turbine blade worked like a pinwheel, getting shoved around by moving air, it would spin slow and weak, and you'd only pull a fraction of the energy out of the wind. The real mechanism has more in common with an airplane wing than with a windmill from a children's book. A turbine blade is an airfoil, curved on top, flatter on the bottom, the same basic cross-section as a wing. Air flowing across that curved surface travels a longer path than air flowing across the flat side, and that difference creates a pressure gap. Lower pressure above, higher pressure below. That gap is lift. On a plane, lift pushes the wing up. On a turbine, the blade is angled so the same force pulls it forward along its rotation instead of upward, and the blade accelerates into the wind almost like it's being pulled around rather than pushed. That's why blade tips can move 4, 5, sometimes 6 times faster than the wind itself. Engineers call that ratio the tip-speed ratio, and most modern blades are tuned to sit around 7 or 8, which means a 20-mile-an-hour breeze can send the blade tip past 140 miles an hour. Nobody stumbled onto this by accident. In 1919, a German physicist named Albert Betz worked out the theoretical ceiling on how much energy any wind turbine could ever pull from moving air, no matter how good the design got. His number was 59.3%. Slow the wind down too much as it passes through the blades and you choke the airflow coming up behind it, stalling the whole system. Don't slow it down enough and you leave energy on the table. Every wind turbine you've ever seen is a compromise built around that ceiling, and the best modern designs land somewhere around 45%, roughly 3 times better than the mechanical windmills that ground grain for centuries on maybe 15% efficiency. The first machine to turn that wind into electricity, rather than just grinding or pumping, went up in Cleveland in 1888. Charles Brush, an inventor who'd already made a fortune off arc lighting, built a turbine 60 feet tall with 144 thin wooden blades arranged in a circle like an enormous bicycle wheel. It produced about 12 kilowatts, barely enough to run a dozen modern hairdryers, and it needed all 144 blades to do it, because nobody yet understood lift the way aviation would teach engineers to a few decades later. Once the Wright brothers and the physicists who studied their wings figured out airfoils, wind turbine design changed completely. Fewer blades, shaped properly, beat more blades shoved around by brute force. Modern blades are grown, not assembled. Each one starts as a mold the length of the finished blade, sometimes over 300 feet long, into which technicians lay sheet after sheet of fiberglass or carbon fiber fabric by hand, soaked in resin and cured under vacuum pressure, into a single continuous shell with no seams to fail under stress. A blade that size can weigh over 40 tons, and moving it from factory to installation site is its own logistical problem, requiring specially designed trucks that can navigate highway curves without swinging the tail end into oncoming traffic, or ships built specifically to carry blades to coastal wind farms where roads were never an option. But shape only helps if the blade is pointed at the wind correctly, and wind direction and speed change by the minute. So the blades aren't bolted in place. Each one sits in a bearing at the hub that lets it rotate along its own long axis, twisting like a propeller adjusting its angle mid-flight. This is pitch control, and small motors inside the hub make tiny corrections every few seconds, reading an anemometer mounted on the nacelle and recalculating the ideal angle in real time. In light wind, the blades pitch to expose as much surface as possible. As wind speed climbs, they twist to spill some of that force before it turns destructive. Past roughly 55 miles an hour, most turbines pitch the blades nearly flat against the wind and lock the rotor entirely, choosing to generate nothing rather than risk tearing itself apart. A turbine doesn't try to catch every gust. It negotiates with the wind, constantly. All three blades bolt onto a central hub, which connects to a shaft running into the nacelle, the boxy housing at the top of the tower that most people mistake for the whole machine when it's really just the drivetrain's shell. That shaft, the low-speed shaft, turns slowly, usually somewhere between 10 and 20 rotations a minute, about the pace of a ceiling fan on low. And that's the problem. 15 rotations a minute isn't nearly fast enough to generate useful electricity. Most generators need to spin close to 1,800 rotations a minute to do their job efficiently. Something inside that nacelle has to take slow, powerful rotation and turn it into fast, weaker rotation, and for most of the industry's history, that something was a gearbox. A traditional gearbox is a stack of planetary and parallel shaft gears working together, multiplying rotational speed by roughly 100, while dividing torque by the same amount, the same trick as shifting a bike into a higher gear. The catch is that a gearbox absorbing the torque of an entire turbine, sometimes equal to the force of several loaded freight trucks pressing down at once, takes relentless abuse, and gearbox failure has historically been one of the most expensive things that can go wrong on a turbine, sometimes requiring a crane tall enough to lift out a component that weighs as much as a school bus. That's why newer designs, especially large offshore turbines, increasingly cut the gearbox out entirely. Direct drive turbines connect the blades straight to an oversized multi-pole generator that produces power at low rotational speeds without ever stepping that speed up mechanically. Fewer moving parts, fewer things to fail, in exchange for a heavier and pricier generator. Whichever path the design takes, it leads to the same part, the generator, and this is where the machine's actual job gets done, turning motion into electricity. The principle underneath it is almost 200 years old. In 1831, Michael Faraday found that moving a magnet near a coil of wire induces an electric current in that wire, a phenomenon called electromagnetic induction. Every generator on Earth, the one in your car, the one in a nuclear plant, the one sitting in that nacelle above the field, runs on that discovery. Inside a turbine's generator, a rotor lined with magnets spins inside a stationary ring of copper coils called the stator. As the magnets pass each coil, they drag the magnetic field with them, and that shifting field pushes electrons through the copper, producing alternating current. Nothing burns, nothing combusts. The only input is motion, and the only output is electrons moving through wire. There's a catch, though. The electricity coming out of that generator isn't ready for the grid. Its frequency and voltage drift constantly as wind speed rises and falls with every gust, while the grid runs on a fixed frequency, 60 Hz in the US, that can't fluctuate without damaging equipment or destabilizing everything connected to it. So before that power goes anywhere, it runs through a power converter, an electronic system that takes the raw variable current, converts it to direct current, then converts it back to alternating current at exactly 60 Hz, synchronized to the same rhythm as every other power source on the grid. That balancing act happens continuously inside a box roughly the size of a shipping container at the base of the tower, while a machine 300 feet above it spins at a completely different, chaotic pace. Wind turbines don't run at full output most of the time, and that surprises people who assume a spinning turbine is always making its maximum rated power. Below roughly 7 to 9 miles an hour, called the cut-in speed, there simply isn't enough force to turn the blades productively, and the turbine sits idle. Between cut-in and somewhere around 25 to 30 miles an hour, output climbs steeply, and past that point the turbine holds steady at its rated maximum no matter how much harder the wind blows, spilling the extra force through pitch control rather than overloading the generator. The ratio between what a turbine actually produces over a year and what it could theoretically produce running flat out the entire time is called its capacity factor, and for a good onshore site that number lands around 35 to 45%, closer to 50 or 60 for turbines out at sea, where wind blows harder and steadier without buildings or hills breaking it up. Keeping one of these things running is a job that still comes down to a person hanging off a rope 300 feet in the air. Technicians climb the inside of the tower on a ladder or ride a service lift, then clip onto the blade itself to check for cracks, erosion, or storm damage, sometimes rappelling down the full length of a blade with a grinder to smooth out pitting caused by rain and hail, hitting the leading edge at over 150 miles an hour, year after year. Every blade has a lightning conductor built into its tip, a metal receptor wired down a copper cable through the inside of the blade to a grounding system buried at the base of the tower. Because a structure that tall, standing alone in open country, gets struck far more often than almost anything around it. In cold climates, some blades carry built-in heating elements to stop ice from building up and flying off in chunks once the rotor spins back up, which is also why turbines in icy regions sometimes shut down and simply wait out a storm rather than risk it. Increasingly, drones fly the inspection routes instead, photographing every square foot of blade surface in a fraction of the time a technician on a rope would need. The sound people associate with wind turbines, that rhythmic whoosh thump, isn't coming from the generator or the gearbox at all. It's aerodynamic, the sound of each blade tip slicing past the tower once per rotation, plus turbulence peeling off the trailing edge, and it carries furthest directly downwind, which is why turbine placement involves modeling exactly how that sound will travel long before a single foundation gets poured. Engineers spend real effort on blade tip serrations, small comb-like edges borrowed straight from owl feather research, because owls fly almost silently by breaking up turbulence at the edge of their wings the same way, and shaping a blade tip to copy that trick can measurably cut the noise a turbine puts out. A turbine like this is built to run for roughly 20 to 25 years, spinning through several hundred million rotations before metal fatigue and wear make replacement cheaper than repair. The tower and the gearbox are mostly steel, and steel gets recycled the way any large industrial scrap gets recycled. The blades are the hard part. That seamless fiberglass and resin shell strong enough to survive decades of stress is also nearly impossible to melt down or separate back into reusable materials, which is why old blades have mostly ended up buried in landfill or cut apart and repurposed into things like pedestrian bridges and playground equipment. Resin chemistries designed to be dissolved and recovered at the end of a blade's life are one of the more active research problems in the industry right now. Height isn't cosmetic either. Wind near the ground drags against trees, hills, and buildings, slowing down and turning turbulent, while wind higher up moves faster and more consistently, something engineers call wind shear. Doubling a turbine's hub height can raise the wind speed it captures by 10% or more, and because the power available in wind scales with the cube of its speed, that modest gain in height turns into a much larger gain in energy. That's why towers have grown from roughly 100 feet tall in the 1980s to well over 300 feet today, some offshore models pushing past 500, each one bolted to a foundation that can require pouring more than 1,000 tons of concrete and steel rebar into the ground, engineered to resist not just the turbine's weight, but the constant twisting force of 3 blades trying to topple the whole structure with every rotation. The scale gets hard to picture. The GE Haliade EX, one of the largest offshore turbines currently spinning, carries blades roughly 350 feet long, close to the length of a football field including both end zones, mounted on a tower that puts the top of the rotor higher than most skyscrapers. One rotation of its blades sweeps an area larger than 5 soccer fields. At the right wind speed, a single turn can generate enough electricity to power a home for close to 2 days. Out where the water gets too deep for a fixed foundation, floating turbines anchor themselves to the seabed with mooring cables instead of concrete, opening up wind resources that used to be permanently out of reach. None of this happens because a machine got lucky at catching wind. It happens because of an airfoil shape studied since the earliest days of aviation, a torque limit calculated on paper in 1919 by a physicist who never saw a modern turbine, a discovery about magnets and copper wire made almost 2 centuries ago, and a long chain of engineering decisions about height, pitch, and gear ratios. each one solving one specific, unglamorous problem, stacked on top of each other for well over a century until the whole system finally worked. Next time you see one of those towers on a hillside or out past the coastline, spinning slow enough to look almost peaceful, remember what's actually happening up there. Air moving at a speed you'd barely feel on your skin is being sculpted, angled, and negotiated with by a blade shaped like a wing, spun into rotation fast enough to be lethal, geared and converted and synchronized through 2 centuries of physics until it comes out the other end as electricity indistinguishable from what's coming out of a coal plant, or a dam, or a reactor. Nobody has to shovel anything into it. Nothing gets set on fire. A 100-ton machine stands in a field or out in open water, catching something you can't see and turning it into something you can't live without. The wind never knew any of that was happening. It just kept blowing, the way it always had, long before anyone figured out how to listen to it.